So we will now go to the different steps of crystallization. Um, we can view nucleation as the part of the crystallization process wherein we have the creation of a crystal, or that's the baby crystal, from a supersaturated solution. So the solution has first to be in supersaturated condition before nucleation would even start. Then we'll have the process of crystal growth. So this is the time wherein your crystal that started growing in the nucleation will grow big in size. So increase of the crystal size up to the desired size by growth from supersaturated solution. Then we have also this case of dissolution. So if our solution will go back to its non-saturated condition or even below supersaturation, there will be a part on those crystals that have already precipitated out or solidified out of their solution to again be dissolved back into the solution, meaning they will start liquefying again. And sometimes this is not avoidable. Now, in the growth process also, we had this what we call Oswald ripening. So it's the slow aging. Actually, the aging of our crystal is a slow process. And this is the size evolution with time of a crystal population in the vicinity of the saturation. So the slow aging or the growing of your crystals is referred to as Oswald ripening. And we have this term agglomeration. So we have agglomeration described here as the formation of crystal clusters linked by crystalline bridges. And this will only occur if our solution is already in supersaturated condition. Now, in terms of crystal growth, in crystallization, growth plays an essential influence on the crystal size and shape. The manner in which the seed crystal is introduced into the solution, and even the manner in which that particular crystal initiates the growth of crystals into desired size and shape, is very important as to the final size and shape of the product crystals. So this growth and how it is allowed to grow in size is very, very important in terms of uniformity of size and shape of our crystals. Then the growth of a crystal face results from, so how does a crystal face grow? So it results from the progressive integration of atoms or ions into the crystal lattice. So it's a progressive integration of atoms into the crystal lattice. That is why it's going bigger in size. Now, the growth kinetic process is divided into, so take note, consecutive steps. So it has to be in following a specific order. And the growth rate is determined by the slowest step, which is referred to as the rate determining step. And this is comparable to any processes, whether we observe in nature and even in the industry. The time that we use or the time that is being used in the production of anything is very dependent on the slowest part of the process. The other parts of the process which are happening or that are spent in a less amount of time does not play a very big role in the total time that is used up in the production of any material. So it is always the slowest part of the procedure that is the determining factor in how long or how much time will there be in producing anything. So it's the same thing with crystals. So the growth rate is determined by the slowest step in the process. Now, if we have the representation of the crystal lattice like this one, so you have a stair, you have steps here comparable to that of a stair, and you have some blocks on the step. So the first thing that will happen here is that, before that, I will discuss what do we call this one. We call this as that terrace. So the terrace or the step. We have a series of steps here. Let's say if we have a stair and we call this one particular step the plain part as the terrace. Now, if we have this as the blocks, they get absorbed on the surfaces. And as such, this particular surface that you're seeing on top is still unfinished because this one part here is still vacant. So what this particular species does is it gets absorbed here, then another one gets absorbed on front of it, then another one gets absorbed until this entire surface here on this particular terrace is complete. And then another one gets absorbed on that other side. Now, this part, which adds up to the length of its step or terrace, is what we call as the step. This one, this part here, we call that the step. Next to that would be the terrace itself. And this corner where your adsorbed species attaches itself, that way this particular step will grow in length until this portion here is the kink. We call that the kink. So the different adsorption sites in our crystal surface, if you will refer to these two steps here as the crystal surface, is the terrace wherein you have a single bond in that case. The step, this one, the step, we have two bonds, this plane and the plane underneath, and then the kink, which has three bonds, this face, and the one below. Okay, these are the three different bonding sites or adsorption sites in our crystal surface, wherein our crystals are growing in size. So the first step in the growth is the transport or the bulk diffusion of the solute ions or molecules towards the crystal surface. So they get to be transferred from the solution, they solidify out, and then gets attached themselves or get to attach themselves on any of the bonding sites that were mentioned in the previous slide. So it could be on the terrace, it could be on the step here, this is the step, and or it could be on the kink, wherein you have three bonds here. On the terrace, you have a single bond, and on the step, you have two bonds. Then they get adsorbed on the crystal surface where there is to be potential growth. So they get to be transported, they get to be transferred here, and they get to be adsorbed on those particular points which I have already mentioned, where they now are considered to be potential growth units. Then we have bi-diffusional diffusion or bi-dimensional rather diffusion of the growth units on the terrace. So bi-diffusional meaning it could be this way or that way. Bi-dimensional diffusion, it could be either that way or this way. And adsorption of the growth unit on a step, so it could be here on the step. And you need dimensional diffusion along the step. So if it's just simply right here on the terrace, that's unidimensional, single bond. Bidimensional here, right here on the step itself. Or it could be in any direction as long as there are two planes in which your particular crystal solute gets attached itself on the surface. And adsorption of the growth unit onto a kink, this red block now is in the most stable condition and it's in being integrated into the crystal lattice. This is the most stable because it's now bonded in this side, on the side there at the back side, and in the bottom part. So that's the most stable bonds. Now, as a consequence of those particular processes in the growth of crystal, there is progressive filling of the step by growth units, progression of the step on the surface, so the steps gets wider and wider, and the formation of the crystal lattice layer by layer. Now, there is a mention about agglomeration and how we distinguish it from aggregation. So there has to be a clear distinction between the two because in here, the term that is used is agglomerate. So when we speak of aggregates, we'll first define aggregation. So it's the formation of a cluster of crystals linked by weak cohesion forces. So the van der Waals forces, aggregation. When we speak of agglomeration, this is collision, then aggregation. So it's composed of these two processes. They collide, then they aggregate. Then this process of collision and aggregation between crystals is followed by the formation of crystalline bridges in supersaturated solution. So there was a mention in the previous slide that agglomeration happens only in supersaturated solution. So there is collision, then aggregation, whereas aggregation is a standalone process. So aggregation is just part of the process of agglomeration. Now, when we speak of aggregate, it's something like this. But when we speak of agglomerate, it's something like this. So there's already a linking of the solids, or of the solids in the crystal. That is why you have the formation already of what we call crystalline bridges, and this will only happen, again as mentioned, if the solution is already supersaturated. So aggregation, there's no linking, but in here, and if there's a linking, that link is very weak. So cohesion forces caused by cohesion forces, but this one is more stable because we have already the presence of these bridges, specifically crystalline bridges. Now we go to the types of crystallizers. So those are just introductory, the process of the formation of crystals, to the actual design of crystallizers. And in terms of the crystallizers, they are actually divided, if I'm not mistaken, to four different groups. And under each groups, we have also different crystallizers classified under each group. So we go first to the cooling crystallizers. Cooling, meaning the process of crystallization, is implied in the name of the group, is through the process of cooling. So we have here in the first type as the non-agitated vessels. So the simplest type of cooling crystallizer, which is in an unstirred tank in which a hot feedstock solution is charged to an open vessel and allowed to cool, often for several days by natural convection. So a cooling crystallizer, can you imagine that, without any form of stirrer or agitation? So it's just let there to stand for several days, and then by the process of natural convection, lower down its temperature and then form crystals. Now, metallic rods, in this case, since there are no stirrers, may be suspended in this solution so that large crystals can grow on them, thereby reducing the amount of product that sinks to the bottom of the unit. So suspended rods, but not stirrers. So there's no moving part in the case of these non-agitated vessels. So the product is usually removed manually, and this is the continuation. Because of cooling, which is very slow, large interlocked crystals are produced, which retain mother liquor, and thus the dried crystals are impure. So take note of this. There are large interlocked crystals, which retains a lot of the mother liquor, and then drying of these crystals produce impure finished products. Impure in the sense that they still have the retained mother liquor on them. Because of the uncontrolled nature of the process, there's no control, there's no steering. Product crystals range from fine dust to large agglomerates. The interlocking here of crystals produce large agglomerates, and as such, the shape and the sizes of the crystals are not uniform, because some are in the form of fine dust while others are in the form of large agglomerates. So labor costs here are high, but the method is economical for small batches. Since capital, operating, and maintenance costs are low, or the production or productivity is low, and space requirements are high. Space requirements are high because the unit in themselves have to stay, shall I say, filled for several days, and then the removal of the finished product with the formed crystals is done manually. So you have to have a lot of space for this crystallizers to house a bigger volume of solution, if that is the solution that you need to be processed is large in volume. Now we go to the agitated vessels, but still under the group of the cooling crystallizers. So installation of an agitator here is to be seen. It's open tank, and it gives smaller and more uniform crystals. So smaller, so no agglomerates. Probably there are, but negligible in terms of the entire volume of crystals that are being produced. So smaller and more uniform crystals and reduced batch times in comparison to the non-agitated crystallizers. Reduced batch times, so meaning we don't have to wait for a long time for the crystals to be produced. Now, because less liquor is retained by the crystals after filtration and more efficient washing is possible, the final product has higher purity compared to the non-agitated vessels. So there is less retention of the mother liquor on the crystals after filtration. Now, water jackets are usually preferred to coils for cooling because the latter often becomes encrusted with crystals and the inner surfaces of the crystallizer should be smooth and flat to minimize incrustations. So we don't want the stirrer or the coil of the cooling medium to be encrusted with crystals nor the surfaces to be encrusted as well. So in this type of agitated vessels, water jackets are the cooling medium. So the vessel in itself is jacketed, wherein water is being introduced on the sides of the vessel or tank, and they are not introduced as cooling medium in the form of coils. Now, operating costs of agitated coolers are high than simple tanks. Of course, it's a given because we have the movement of the stirrer. Although the productivity in this case is higher and product handling costs are still high. Now, this is in the case of the your cooling agitated crystallizer. So there's an agitator in the middle to ensure that there will be fast cooling. If there is fast cooling, then there will also be a fast production of crystals, even growth of crystals also. Now, under the cooling crystallizers, we have the third type, which are the scraped surface crystallizers. So the Swenson-Walker scraped surface unit, which is used for processing inorganic salts that have a high temperature solubility coefficient with water. Now, these are shallow, semi-cylindrical trough, about 600 mm wide and 3 to 12 meters long, fitted with a water-cooled jacket. So just like your cooling agitated crystallizer, the form of cooling here is in the form of jacket, or the design of the cooling mechanism is in the form of a water-cooled jacket. There's a helical scraper rotating at 0.8 to 1.6 Hz, keeping the cooling surfaces clean and enhances growth of crystals by moving them through the solution which flows rather down the sloping trough. So the trough in itself is sloping downwards. That way, the solution that has already the solids on them gets to uh, be removed in the crystallizer by the process of gravity or through the process of gravity. They are usually mainly for processing fats, waxes, and other organic melts. So take note of the application of the Swenson-Walker scrape surface crystallizers. And actually, these particular crystallizers are the ones that are given in the board exam in terms of the design. And this is an example of a Swenson-Walker crystallizer. So it has a cooling jacket that ensures that the solution inside is cooled. And we have the sample problem number 4 for the Swenson-Walker crystallizer. So a solution containing 23% by mass sodium phosphate is cooled from 313 to 298 Kelvin in a Swenson-Walker crystallizer to form crystals of sodium phosphate, what's a 12? Deca. After deca, we have 11, 12. We have already, this is already hydrated, so I forgot how it is called. 12. The solubility of sodium phosphate at 298 Kelvin is 15.5 kilograms of the solid per 100 kilograms of water. And then the required product rate of crystals is 0.063 kilograms per second. The mean heat capacity of the solution is 3.2 kilojoule per kilogram degree Kelvin, and the heat of crystallization is 146.5 kilojoule per kilogram. If cooling water enters and leaves at 288 and 293 Kelvin respectively, and the overall coefficient of heat transfer is 140 watt per square meter degree Kelvin, what length of crystallizer is required, assuming area available is 1 square meter per length or per 1 meter length of pipe. So we will assume that a 1 meter length of pipe will have this available area for heat transfer. So we are to solve the length of the Swenson-Walker crystallizer, or the length of the crystallizer in this case, that would be required to, of course, produce this much of crystal, 0.063 kilograms per second. We will start with the illustration of this in the form of the illustration that was given in the PowerPoint. The crystallizer is simply drawn in the form of a box, and the streams that are important with their corresponding data should also be depicted on such illustration. So I will stop sharing here and I'll go to the board which we can use. Wait, I don't have any board here. Wait. My gosh, I can't find my board. Now wait. Hmm, why can't I find it? Okay. If we get disconnected, we'll just click again the same link. Okay, I will start sharing again. Okay, I will not go back to the slide anymore to save us time. So I will simply draw here, illustrate to you how you're going to draw the crystallizer and depict the data that is given in the problem. So our crystallizer, as I said, will be drawn only in the form of a rectangle, just like the one you saw on the slide. So we'll have a rectangle for our crystallizer. And we have the feed, and I'll have here water evaporated just in case there is. So we'll go back later to the problem. If there's a mention of water evaporated, this is our crystallizer. And you have here the magma, which is composed. So let's say this is M, which is composed of our liquor and our crystals. So in our case, the crystal is sodium phosphate. If this is sodium phosphate, this should be 3. Sodium phosphate, it's already in the hydrated form here. It's not a decahydrate actually, it's a 12. that's our crystal. And it was mentioned in the problem that the rate of product production or removal is 0.063 kilograms per second. I like to read that part of the statement so that you will understand why it's the way it's reflected there. It says here that the required product rate of crystals is 0.063 kilograms per second. So that's the output that is being required, so that the problem is now asking what should be the length of such a crystallizer that will be producing that much of crystals. Okay, now we go back here, and then it's given that the cooling of the feed, so this is our feed, is from an initial temperature of 313 Kelvin and a final temperature of 298 Kelvin. So true to the process of cooling, your feed decreased in temperature from 313 to 298. Your feed here consists of 23% by weight sodium phosphate. By the way, this is the given information. Okay. If how do we put the 23% weight sodium phosphate there? So the problem stated that a solution containing 23% by mass sodium phosphate is cooled from 313 to 298 in the crystallizer to form crystals uh, of sodium phosphate 12 water molecules. Okay, the heat capacity of the solution is 3.2. So it's stated here, it's 3.2 for the heat capacity. So it's referring to the solution. So it's the thing inside the crystallizer. So I'd like to place here 3.2 kilojoule per kilogram Kelvin. Then you are given the heat of crystallization in the problem, which is 146.5 kilojoule per kilogram Kelvin. Now, cooling water is introduced in the crystallizer, so we'll have, so this means there's cooling water here, and the initial water temperature here is 288 Kelvin, and after it cooled down the solution inside the crystallizer, its temperature increased to 293 Kelvin. Let me check. So from 288 to 293. So it says here, if cooling water enters and lives at 288 and 293, and the overall heat transfer coefficient is 140, so that's something that we need to add here, the U. So 140 watt per square meter Kelvin. You are asked to determine the length of the crystallizer that will produce this much of crystals, okay, in the form of this hydrated sodium phosphate. Now, if you are to look for the length, it's already designed. You are to think right away, just like the way I taught you to find your way through the required with heat transfer problems. Then you are to think of what available formula you can use that will lead you to the length. Okay, so since so far you've only learned heat transfer, and if I will ask you what should that formula be that will point you out to the length of the crystallizer, what formula will point you to the length of the crystallizer? And you have learned that formula because it's a standard formula for heat transfer. What do you think is that formula? would be for heat transfer. If you're designing and you are to know the length of the of anything that where heat is to be transferred from or to, that would be Q. This is heat transfer. We haven't yet touched mass transfer. A delta T log mean. Okay, I use the delta T log mean. You may wonder why you use delta T log mean. You have to go back to the given. You're given the temperature of the feed from the initial process of cooling and after, and you're given the temperature of the cooling medium. All temperatures are in place. So whenever you have such, you will use delta T log mean. You will not use effectiveness in determining the Q, as discussed to you under the topic of heat transfer. Now, why did we have to start with this formula? Because the length of the crystallizer actually can be taken from the area here. Knowing that if the crystallizer is cylindrical in nature, your heat transfer area is the circumference times the length of the said cylindrical surface, so 2 pi dl. If I know the area, I get to solve for the length because it's pi dl as I've said. So for me to be able, or for us to be able to determine the length of this particular crystallizer that the problem is asking from, the thing that we need to know is the area. So this is your main goal. You find this area, you find